All right, so this is 12-1 probability, and I apologize for length of these notes. I'm kind of constrained on time. That's what it's boiling down to. So we have the probability of mutually exclusive, which are independent or disjoint events, overlapping events, and independent events. Sorry, that should say dependent. That needs to be fixed right now before I do any more work. Dependent. All right, cool. All right, so our vocabulary here is going to be probability. Probability is the likelihood of an event happening. That's what it is the chance of an event happening. It is a number between 0 and 1, or 0% through 100%. It cannot exceed 100%. It cannot be less than 0%. And mathematically, we can loosely say it is the number of ways a desired outcome occurs over the total number of possible outcomes or events. Might use the word event. Lots and lots of ways of writing that thing. So insert shape, need a line, need that divisor. And that's usually how you find the probability of an event. We have what's called a mutually exclusive event. These are also known as independent events. These are events that do not influence each other or have what we call overlap, which means basically there is no way that each event can happen at the same time, just not possible. Then you have dependent events, which is not mutually exclusive, and I never defined overlapping here, which I probably should. Dependent events are events that can influence each other. They can, not necessarily, but they can influence each other. May not in a text. And sometimes this involves overlap, and sometimes it does not. Overlap's kind of an interesting concept, and we will talk about overlap. All right, so Jimmy has a spinner with the numbers 1, 5, and 8 and a 6-sided die. A sample space of all possible events would look like this. And I got off in the text box. Sample spaces are something most people gloss over and they refuse to think about. They are somewhat time-consuming to make, but they are always right. There are formulas and shortcuts, but if we don't think about the sample space of an event, we will likely miss something. You will. Anywho, so here's a sample space. You could spin a 1 and you could then roll a 1 through a 6, because I kind of expect you to know that a 6-sided die, you may not know this, but 1, of course, usually it doesn't have 1s, 2s, and 3s. It's usually got the dots or whatever, but there's 6 numbers on a 6-sided die. And it occurs to me, last year was the first year I really noticed this, but an alarming number of kids don't know what a spinner looks like. So let me make you a spinner. That was way too close. That's what I need. And this spinner has 1 and a 5 and an 8 on it. And then you got a little arrow that you thump. And it goes around and around and stops on a number. So find the probability that Jimmy spins a 5 and rolls a 5. Now, the nice thing about sample spaces is I can see it right there. It's one event out of 18. Okay? And there are other ways of getting this. Okay? There's a formula, and we learned that the word and means multiply. And I'll come back to this example when I talk about the formula. He spins a prime number and rolls an even number. So I know that primes are an issue. Primes are any number divisible by themselves and one only. The first one's 2. It goes 2, 3, 5, 7, 11, ... But he spins a prime number. So your primes are, he spins a prime. 1 is not prime. 8 is not prime. These are the primes. So he spins a prime and rolls an even number. That'd be that guy, that guy, that guy. This is 1, 2, 3 events out of, how many were there again? 18, which is 1 in 6. So I think on the next slide I talk about some formulas, and we'll go back and look and see how we do these. Yeah, we're going to talk about them. So in the previous example, we were spinning the spinner and rolling a die. Are these independent? And it should say, are these independent, which means mutually exclusive, disjoint, dependent, or overlapping events? These are independent events. What you spin on a die does not influence what you roll. Sorry, what you spin on a spinner does not influence what you roll on a die. And if you've never seen Venn diagrams, I'll talk more and more about them. But this is your spinner, the probability of rolling a spinner, and the probability of rolling a die. There's no overlap. And you'll see what overlap looks like on a Venn diagram before too much longer. There are formulas for independent events, which we also call mutually exclusive. And another word that is used commonly is called disjoint, because they're not connected in any ways. They're not jointed together. And there's 2 of them. The probability of event A or B happening, which is also written using set notation as A union with B. Remember that guy? Has a formula, and the probability of A or B happening is the probability of event A plus the probability of event B. When you talk about independent events, you kind of need to establish that the word or means add, plus. And the probability of event A and B, which is also written like this, it's the upside down union. I literally read these A and B. At least that's what I think in my head. It helps me memorize which one it is. But the probability of A and B happening is the probability of event A times the probability of event B. Now, I'm going to type out here. So how we read things is big. Most kids read these things just horrible. But this is red. The probability of events A and B happening is equal to the probability of event A times the probability of event B. Friday, when we start working on this in class, kid will be like PA, PB, and I'll be like, ugh, you know nothing. So anyways, let me go back to my die here. This was an and, so this was the probability of spinning a 5 and rolling a 5. Okay, so it's going to be the probability of spinning a 5 and probability times, not and, sorry, times the probability of rolling a 5. Now, if you talk about this spinner, your probability of spinning a 5 is 1 in 3. And the probability of rolling a 5 is 1 in 6. And if you know anything at all about fractions, you know that 1 times 1 is 1 and 3 times 6 is 18. It's the exact same thing. The formulas are shortcuts to sample spaces. He spins a prime number and rolls an even number. Well, the prime numbers of spinning is 1 and 3. It's 1 and 3. Then times an even number. On a 6-sided die, there are 3 of 6 even numbers, or 1/2. But anyways, 1 times 3 is 3. 3 times 6 is 18. And it's the same exact proportion, 1 to 6. Or ratio should be the right word. Determine if the 2 events A and B are independent of each other. So it's really, really simple. 2 events are independent if the probability of A and B is equal to the probability of A times the probability of event B, or the probability of A and B is equal to the probability of A plus the probability of B. By all means, write these things down. until you have them memorized. That's how you memorize. You just keep writing and you think while you're writing. So I'm going to see what the numbers work. So let's take the probability of A and let's multiply it by the probability of B because this means and, okay? That'd be 0.2 times 0.3, which is not 0.6, it's 0.06. I know you'll be like, oh, no, about that, Milbrath. No, I'm right. Which is not 0.4. So these events right here, they are not independent. They are something else. They might be dependent. They might have nothing at all to do with each other. Couldn't tell you. All right, the union sign actually means or. The probability of A or B is 9/10. And the or statement, that should say or. I don't know why I wrote and. The or says if you take them and add them together, you should get 9/10. So 0.5 plus 0.4 equals 0.9, which is true. These are independent. Because, and I know you don't want to see me just writing this, the probability of A plus the probability of B is equal to the probability of A or B. Moving forward. A standard 52 card deck contains 52 cards. There are 4 suits. The black suits are clubs and spades. The 2 red suits are called hearts and diamonds. Each suit has 13 cards numbered 2 through 10, a jack, a queen, a king, and an ace. Find the probability that Billy draws a 3, then a queen, and then a black card. So there's an order here specified. Every time he draws a card, he places it back in the deck. So what we have here is we have a compound and situation. This is the probability of a 3 and a queen and black. And he puts the card back in the deck, okay, which is a big deal. He puts the card back. So if you think about your individual probabilities, the probability of getting a 3, there's going to be 4 3s in a deck of cards. That's 4 out of 52, which is 1 in 13. The probability of getting a queen, there are also 4 queens because every suit has a queen. It's also 4 in 52, which is 1 in 13. Half the cards in a deck of cards are black. So the probability of being black in a deck of cards is 1/2. And because of the way this is laying out, it's an and situation. And means the word multiply. So I'm going to take a 13. I'm going to multiply it by another 13. And I'm going to multiply it by 1/2. And 13 times 13 is 169. If I double it in the bottom, I'm going to have 338. Seems right. 169, 320. Yeah, 328. 338. So there is a 1 in 338 situation of this possibly happening exactly like that. And again, for those of you who don't listen, that was supposed to be 338. All right, find the probability that Billy draws 2 aces in a row, followed by a king without replacement. So the first time you draw an ace, there's 4 of them. The next time there's 3 of them, okay? There were 52, you didn't put back, there's now 51. And now you draw a king. Well, there's still 4 kings in the deck, but there's only 50 cards left. That's what we're looking at here, okay? You got to think about that. And this is kind of another layout. I draw an ace and an ace and a king. These are all multiplication ideas. So it's going to be 4 and 52, which I've reduced before. 4 out of 52 is 1 in 13, right? So it's 1 in 13 times 3 in 51 times 4 in 50. I can reduce that. That's 2 in 25. And even with them reduced, I don't care to do the math. I can do the top. 1 times 3 times 2 is 6. The bottom, 13 times 50. Y'all probably don't do things like that, do you? You can tell I'm old school. The bottom is 16,575. And does that reduce? 6 in that. It might reduce. I don't think it will. I did. 2 in 5,525. 2 in 5,525 chances of happening. Pretty slim. Find the probability that Billy draws an ace or a jack and then a king without replacement. So there's a couple ways of doing this. There really are. I can get to this one real quick. If I talk about ace or a jack, I'm kind of thinking adding. There's 4 here and 4 there. That's 8 cards, right? That's 8 in 52. He's going to get a jack, ace or jack, 8 out of 52 chances, all right? And then a king without replacement. Now, he picked one of those 2 cards. He wants a king, of which there are 4, but now the denominator is changed to 51. You have to think about things. This last example is a good example of overlap, and I'm trying to show you how to not do it with overlap. I can tell you right real quick, this is 1 in 51. And the reason I know that is because 8 times 4 is 32, so I have 32 over 32 times 51, 32's cancel. So 1 in 51 chance of happening. All right, moving forward. I mentioned that the last one had some overlapping events because it said something or something, and there was overlap there. And there's another way of doing that problem. I'm not going to go back and do it though. But overlapping events are events that have shared space. That's all they are. Nothing more. There are probability formulas for overlapping events. One of them is probability of A and B, and they're a little bit different. This, again, remember, can be written, and I keep writing this, and I'm hoping it'll stick with you. A and B is the probability of A union, not union with B, but A and B. A or B is the probability of A union with B. Now, A and B is actually what we call the overlap. That is what is called the overlap. But anyways, it has a formula. The probability of events A and B for situations where you have overlap is the probability of event A plus the probability of event B minus the probability of both. And again, we refer to this piece as the both part. Okay. The probability of A or B is actually, you can derive it from this one. You just switch this guy over here and bring that guy over there. Probability of event A or B happening is the probability of event A plus the probability of event B minus the probability of event A and B. And I know a lot of y'all don't like probability, and there's nothing I can do about that. Absolutely nothing. I wish I could. But if we have 2 circles here that represents events A and B, this little space right here is the both part. That is the probability of both happening. It is the overlap, and overlap is the both piece. I can't remember if I have any Venn diagram examples in these notes or not. If not, they need them. But I think I put one in. Good. Probability that it will rain Thursday is 25%. The probability that it will rain Friday is 45%. The probability that it will rain both Thursday and Friday is 20%. Find the probability that it will rain Thursday or Friday, but not both. That would be an and statement. Weather is dependent. And it has overlap. Because when it's wet, it stays wet. Those influence each other. When it's dry, it stays dry. You've been around long enough to realize that, okay? Weather is a dependent situation. It depends on the previous day's weather. Now, we're going to use our formulas here. I want to find the probability that it will rain Thursday or Friday. So the probability of Thursday or Friday is not just as simple as adding. For one, there's not enough information on the text. It has got to be based on our previous formulas, the probability of Thursday plus the probability of rain on Friday minus the probability of rain on both Thursday and Friday. Okay? Now, the probability of rain on Thursday is 25%. The probability of rain on Friday is 45%. And the probability it's going to rain on both days is 20%. And that's going to give me the probability of rain on Thursday or Friday just by doing a little basic math. So 25 and 45, if you put them together, is going to be 70. 70 minus 20 is 50%. There is a 50% chance that it will rain Thursday or Friday, not both. Now, let me talk about a Venn diagram. The same problem with the Venn diagram. The key on the Venn diagram is to put the and statement in first. 20%. Now, it told you in the text that the probability of rain on T was 25%. So even though visually this isn't appropriate, because this is 20, this has to be 5, because together they have to make up to 25. The probability of rain on Friday was given in the text as 45. And you've already accounted for 20%, so there needs to be 25% left over. And I just went kind of blank here. Oh, now I want the probability of rain on Thursday or Friday. I just add all these numbers up. 5 plus 20 is 25, plus 25 is that 50. So a Venn diagram works very well on overlapping probabilities. All right, term of the events are independent or dependent. And again, this really just focuses on knowing your stuff, okay? So I'm going to take 0.3 and 0.3 and multiply them together and see what I get. If I take 0.3 and I multiply it by 0.3, I get 0.09, which is cool. This means independent because the probability of A and B happens to be equal to the probability of event A times the probability of event B. All right, now this one has given me a whole heck of a lot more stuff. It's given me an or statement, an and statement, an individual statement. So I'm going to check this. I'm going to check the probability of A or B. And it should be equal to the probability of event A plus the probability of event B minus the probability of events A and B. So A or B is this guy, it's 0.5. It should equal 0.35 plus 0.45 minus the and statement, the overlap of 3/10. So 0.5 should equal 0.8 minus 0.3, and in fact 0.5 does equal to 0.5, so true. Because that was true, the events are, and I wish I hadn't used the word, the events are dependent / overlapping. I'm going to say overlapping and possibly dependent. Overlapping events are not necessarily dependent upon each other. There are situations, rare as though they might be, where they are not dependent upon each other. Anywho, order is a big thing in probability. Consider the two following examples. What is the probability that Billy draws a king followed by a black card and let's say without replacement? All right. Okay. So you'd be very, very tempted to look at this, and these are kind of thinking problems. There's more than one situation that's possible. Billy draws a king. Well, that's going to be 4 and 52, followed by a black card, which means we have the and statement because it's king and black, okay? Now, here's where it gets fun. What if he didn't draw a black king? Okay, so if he didn't draw a black king, there's still 26 black cards in the deck out of 51. What if he did? So if he did draw a black card the first time, which was a king, no matter what, 4 and 52, the next time he draws, there's only 25 and 51. Kind of interesting, huh? What you're actually dealing with here is two situations. I can be this situation or this situation. And I'm going to write that on words. Maybe that'll help you comprehend what I'm trying to tell you. But here's what happens. We draw a non-black king and then a black card, or we draw a black king and then a black card. Now, notice I'm using the word or here. That means that I need to be doing some adding. These two pieces, they have to be added. They have to be added. So I get to go push some buttons in the TI-84. Now, I know that 4 out of 52 is 1 in 13. So I got a 1 in 13 times a 26 and 51. I'm going to go ahead and convert that to a fraction. That piece becomes 2 51st, all right? I also have a 1 in 13. Use parentheses here. You don't have to have parentheses. I have a 1 in 13 times a 25 and 51. And I'm going to go ahead and hurry up and make my calculation. Sometimes when you're working with calculators, you have to put things in fractional form real quick or they lose too much when they round. I'm going to add those two fractions together, and I got 1 in 13 chance. There are other ways of doing that. There's lots and lots of ways of doing that. I like this approach where I think, and I was thinking about a sample space, believe it or not. I was thinking about possible outcomes. I was legit thinking about a sample space. All right, what is the probability that Billy draws a king and an ace and a jack? This problem is not too bad. A king and an ace and a jack. So it's a 4 in 52 times an ace, which is 4 out of now 51, times a jack, which is now 4 out of 50. Like that one's straightforward. Whatever that ends up being. I'm not going to waste your time on that. The last thing we need to talk about today is what's called the complement of an event. So the complement of an event is the probability that an event does not happen. Okay, so here's how we write it out. If the probability of an event A is going to happen, then the probability, so I guess I should just define it. Complement of event A happening is 1 minus the probability of event A happening is 1 minus A. So that means since they're not happening, it's 1 minus A. Now, why 1 minus A? Because that's 100% minus the probability of that event happening. That means they're not going to happen. And we write that kind of funny. We call the complement of an event A with a bar over it. So the complement of event A is simply 1 minus the probability of event A. So if the probability of event A is 5/27, what is the complement of event A? Notice how I read that? What is the complement of event A? Well, it's pretty simple. It's got to be 1 minus 5/27. So let's just go old school here. We have to have common denominators and all that stuff. You should agree with me that 27 over 27 is 1. And 27 minus 27 sevenths minus 5/27 is going to be 22 27ths. That's how hard that is. Here's another one. 2 6-sided die are rolled. Find the probability that the sum is not 7. Okay. This would be the complement of a sum equaling 7. That's what it is. The complement of a sum equaling 7. So there's a couple of ways of getting to a 7. let's think about all the ways we get to a 7. We could have a 1 and a 6. We could have a 2 and a 5. We could have a 3 and a 4, right? That'll get me to a 7. What else could we have? We could have, looking at it that way, that's first one. We could have also flipped the script. We could have a 6 and a 1. We could have a 5 and a 2. And we could have a 4 and a 3. There's 6 ways this happened. Okay. Now, some teachers might teach that, and it's kind of apparent here, the odds of getting a 1 are 1 in 6, followed by a 6, also 1 in 6. This is 1 in 36 chance of happening. Each one of these things has a 1 in 36 likelihood of happening. So what I encounter is I have 6 things with a 1 in 36 chance of happening. So the probability of a sum of 7 is actually equal to 6 in 36, or 1 in 6. The probability of not 7, its complement, I'm just going to put a bar over that, would be 1 minus 1/6, which is 5/6. And this would have been a very good problem to go back and look at the sample space. I highly encourage you to do that. Look at the sample space and think about what actually we didn't have a sample space for that, so never mind. But it's a good one to lay out the sample space. I just didn't want to do it. The last couple of things in your notes are for y'all. And it's mainly there for me to go over in class with you on Monday. But hopefully you try to do them. And again, I apologize for how long that video is. I can't break this section in 2 days. It's not that I didn't want to, I just couldn't.